When service entrance conductors are installed in parallel, determining the appropriate size of the equipment bonding jumper on the supply side of the service equipment is crucial for ensuring electrical safety and compliance with the National Electrical Code, specifically Section 250.102. The fundamental principle governing this sizing is that the equipment bonding jumper must be capable of safely carrying the maximum fault current that could occur in the system. To achieve this, the code mandates that the size of the equipment bonding jumper is based on the equivalent sum of the ampacity of the paralleled conductors, rather than the individual conductors. This means you treat the group of paralleled conductors as a single conductor with a combined ampacity equal to the sum of the individual conductor ampacities. Here's a detailed explanation of the process. Firstly, determine the total ampacity of the paralleled conductors. If you have, for example, 4 500 kc male conductors in parallel for each phase, you need to find the ampacity of a single 500 kc male conductor from the appropriate table in the NEC, such as table 310.16, and then multiply that ampacity by 4. The resulting value is the total ampacity of your paralleled conductor set. Secondly, once you have the total combined ampacity, you can use NEC table 250.102 C1 to determine the minimum required size of the equipment bonding jumper. This table provides a direct correlation between the size of the service entrance conductors and the required size of the equipment bonding jumper, based on the material of the conductors and the bonding jumper, whether they are copper, aluminum, or copper-clad aluminum. Thirdly, it is important to consider the material of your conductors and the bonding jumper. The NEC differentiates between copper, aluminum, and copper-clad aluminum conductors when determining the required size of the bonding jumper. The ampacity of aluminum conductors, for instance, may require a larger bonding jumper size compared to copper conductors for the same ampacity. Fourthly, remember that table 250.102 C1 provides the minimum size requirement for the equipment bonding jumper. In some cases, engineering judgment or local regulations might necessitate the use of a larger bonding jumper to ensure a lower impedance grounding path or to provide additional safety margin. Fifthly, consider any applicable notes associated with table 250.102 C1. These notes often provide clarifying information or exceptions that could affect the sizing calculation. For example, there might be allowances for using smaller bonding jumpers under specific conditions, provided that the grounding impedance is sufficiently low. Sixthly, ensure that the equipment bonding jumper is properly installed and terminated. The effectiveness of the bonding jumper relies not only on its size but also on the quality of its connections. Terminations must be made using approved methods and hardware to ensure a low impedance connection. Seventhly, documentation is key. Keep a record of all calculations and the basis for selecting the equipment bonding jumper size. This documentation will be invaluable for inspections and future reference. Eighthly, it is always advisable to consult with a qualified electrical engineer or inspector, particularly for complex installations or when there is uncertainty about the code requirements. They can provide expert guidance and ensure that the installation meets all applicable standards. Ninthly, consider the available fault current at the service equipment. Although table 250.102 C1 provides a minimum size, a more detailed analysis of the fault current might reveal the need for a larger bonding jumper to withstand the thermal and mechanical stresses imposed by a high magnitude fault. Tenthly, when dealing with paralleled conductors, ensure that each conductor is properly sized and installed according to NEC section 310.10 H, which covers the requirements for paralleling conductors. This includes ensuring that all conductors are the same length, conductor material, circular male area, insulation type, and are terminated in the same manner. Let's delve deeper into specific aspects and clarify potential areas of confusion. Consider a scenario where you have 3 sets of 500 kc mil copper conductors paralleled per phase. According to table 310.16, a 500 kc mil copper conductor has an ampacity of 380 amps, assuming it's rated for 75 degrees Celsius termination. Therefore, the total ampacity for each phase is 3 multiplied by 380, which equals 1140 amps. Now referencing table 250.102. C1, we look for the conductor size that corresponds to 1140 amps. Since 1140 amps falls between the ranges provided in the table, we would typically round up to the next available conductor size listed. If the table shows that for conductors over 1100 amps but not over 1200 amps, a minimum equipment bonding jumper size of 3/0 copper is required, then you would select a 3/0 copper conductor as your equipment bonding jumper. Aluminum or copper-clad aluminum conductors will typically require larger sizes. For instance, using the same 1140 amp service entrance, but with aluminum conductors, table 250.102. C1 might specify a 4/0 aluminum conductor as the minimum required size for the equipment bonding jumper. The NEC emphasizes the importance of maintaining a low impedance ground fault current path. This low impedance is crucial for facilitating the operation of overcurrent protective devices, such as circuit breakers or fuses, in the event of a ground fault. A properly sized equipment bonding jumper contributes significantly to this low impedance path, ensuring that fault currents are quickly and effectively cleared. Moreover, the equipment bonding jumper plays a vital role in minimizing touch potential, which is the voltage difference between metallic equipment enclosures and ground. By bonding these enclosures to ground, the equipment bonding jumper helps to equalize the potential and reduce the risk of electric shock to personnel who might come into contact with the equipment during a fault condition. Understanding the terminology used in the NEC is also important. The equipment bonding jumper is a conductor that connects the service equipment enclosure to the grounded conductor of the service. Its primary purpose is to provide a low impedance path for fault current to return to the source, thereby tripping the overcurrent protective device. It is distinct from the grounding electrode conductor, which connects the grounded conductor to a grounding electrode, such as a ground rod or a metal water pipe. While both conductors contribute to the overall grounding system, they serve different functions. The NEC also addresses the issue of conductor ampacity adjustment and correction factors. These factors are applied when conductors are installed in conditions that affect their ability to dissipate heat, such as when they are bundled together or installed in a high ambient temperature environment. When applying these factors, it is essential to ensure that the conductors still have sufficient ampacity to carry the intended load. The ampacity of the conductors after applying adjustment and correction factors must be used when sizing the equipment bonding jumper. In summary, sizing the equipment bonding jumper for paralleled service entrance conductors involves determining the total ampacity of the paralleled conductors, consulting table 250.102. C1 to find the minimum required size of the bonding jumper, considering the material of the conductors in the bonding jumper, and ensuring that the bonding jumper is properly installed and terminated. Adhering to these guidelines will help ensure a safe and code-compliant electrical installation. Always consult the latest edition of the NEC and local regulations for specific requirements. Remember to always prioritize safety and consult with qualified professionals when designing and installing electrical systems. Ignoring these rules can lead to safety hazards and code violations. When using table 250.102, C1, it is important to understand that the table provides minimum sizes based on the ampacity of the service entrance conductors. The table is based on the assumption that the service entrance conductors are sized according to the requirements of Article 310 of the NEC, which covers conductor ampacity and installation requirements. If the service entrance conductors are oversized for any reason, the equipment bonding jumper can still be sized based on the actual ampacity of the conductors, not the size of the overcurrent protective device. The NEC also addresses the use of listed equipment. If the service equipment is listed and labeled, the equipment bonding jumper must be sized according to the manufacturer's instructions. The manufacturer's instructions may require a larger bonding jumper than what is specified in table 250.102. C1. In addition to the equipment bonding jumper, the NEC also requires a main bonding jumper to connect the equipment grounding conductor to the grounded conductor at the service. The main bonding jumper is sized according to Table 250.28, Seat 1, which is similar to Table 250.102, Seat 1. The size of the main bonding jumper is based on the size of the service entrance conductors. It is important to ensure that both the equipment bonding jumper and the main bonding jumper are properly sized and installed. Both jumpers play a critical role in providing a lower impedance ground fault current path. Moreover, it is important to understand that the grounding system is not intended to carry current under normal conditions. The grounding system is only intended to carry current during a ground fault. The purpose of the grounding system is to provide a low impedance path for fault current to return to the source, thereby tripping the overcurrent protective device. If the grounding system is carrying current under normal conditions, this indicates a problem with the electrical system. It could be a sign of a ground fault or a neutral to ground fault. Any such problems should be investigated and corrected immediately. Always remember that electrical work can be dangerous. It is important to take all necessary safety precautions when working on electrical systems. This includes wearing appropriate personal protective equipment, such as safety glasses and gloves, and energizing the circuit before working on it. If you are not qualified to work on electrical systems, you should hire a qualified electrician. Additionally, when dealing with older electrical systems, it is important to inspect the existing grounding system to ensure that it is still in good condition. Over time, grounding conductors can corrode or become damaged, which can compromise their effectiveness. If the grounding system is found to be in poor condition, it should be replaced or repaired. The NEC also provides requirements for the installation of grounding electrodes. Grounding electrodes must be installed in accordance with Section 250.52. Common types of grounding electrodes include ground rods, metal water pipes, and concrete encased electrodes. The NEC specifies the minimum size and length of grounding electrodes, as well as the methods for installing them. It is important to follow these requirements to ensure that the grounding electrode is effective. In addition to grounding electrodes, the NEC also requires the use of bonding jumpers to bond together all metal parts of the electrical system. This includes metal conduits, metal enclosures, and metal equipment. Bonding jumpers are used to create a low impedance path between these metal parts, which helps to equalize the potential and reduce the risk of electric shock. The NEC specifies the minimum size of bonding jumpers, as well as the methods for installing them. Ultimately, understanding and applying the principles of grounding and bonding is essential for ensuring the safety and reliability of electrical systems. By following the requirements of the NEC and consulting with qualified professionals, you can help protect people and property from the hazards of electricity.